Okay, so in the last lecture we introduced p-adic completion of a general number field and we proved a bunch of properties about them. We will continue our study of p-adic completions of number fields and give a second description of this today. Recall what we did last time. So, we had this picture where P sub P is a ideal in P, which is a subring of K sub P. This contains K, this contains OK, and there is P in here, right. And we proved that OK mod P is isomorphic to OP mod P sub P. Okay. In particular, so if yeah, okay. So let me give the following as an exercise. This is just like last time I gave. So exercise, prove that OK, OP mod P sub P to the n is isomorphic to OK modulo P to the n. Okay, so this isomorphism that we got mod P, it extends to an isomorphism modulo P to the n. Okay, so if alpha is an element of O sub P, then we get a sequence of elements alpha 1 and so on in K, in OK, satisfying the following. Well, alpha n is congruent to alpha modulo P to the n, or P sub P to the n to be technically correct. But furthermore, alpha 1 mod P, it contains alpha 2 mod P squared, which contains alpha 3 mod P cubed, and so on. Okay. So, you get a nested sequence like this. So, what I do is I let beta 1 up to beta, I don't know what to call it, let us say m, be representatives of OK mod P in OK. So, I am taking elements of OK that represent each equivalence class modulo P, and let pi be an element in P that is not in P square. Okay. Then pi to the n minus 1, beta 1 up to pi to the n minus 1, beta m are representatives of elements in P to the n minus 1 modulo P to the n. Okay. There is a isomorphism between OK mod P and P to the n minus 1 mod P to the n. Right. This is we looked at this a long time ago, and so that gives you this statement. It is not entirely clear if you do not remember that. So, I encourage you to prove this yourself, or at least deduce it from what we have done before. Okay. All right. So, therefore, alpha can be written as alpha is summation I going from 0 to infinity a I pi I where AI is in this set beta 1 up to beta m. Okay. Any element can be written like this. Furthermore, alpha I is summation, or maybe I'll call it alpha j is summation I going from 0 to j ai pi to the I. Okay. So, clearly this is an element in OK. Now, similarly, any element of k sub p can be written as summation I going from minus n to infinity ai pi to the I, where again ai is in beta 1 up to beta m. All right. Okay. So, these KPs, so here is a remark, these are what are called local fields. So, these are local fields. So, if you hear the term local fields, now you know what it means. Okay. Our real numbers and complex numbers are also local fields, but they are Archimedean local fields. These are non-Archimedean local fields. Okay. And the reason why we define them is so that we can do analysis on them, right. But analysis on p-adic fields is much easier than analysis on real numbers, and we will see examples, we will see results that will justify my statement. But let us before going to that, let me prove what is called a product formula. This is very easy to prove, but extremely useful tool. So, let k be a number field, okay, and we have the following completions of k. We have the following completions of k. Okay. So, 1, we have Kp for all non-zero prime ideals P of OK, and we normalize this by, so you take alpha p, this is norm of p to the power minus m if p to the m is the largest power dividing alpha. So, we always normalize it in this particular way. You can change the constant that you can take something equivalent and that will change it to a different valuation, but different but equivalent valuation. Now, sigma from k into r gives completion r, and we normalize it as follows. Yeah, it is usually customary to denote these places as V. So, let me say V alpha sub V. This is you take the embedding V of alpha and you take the mod of that, right. So, that is how I normalize this, or you take V from k to c such that V of k is not contained in R. This gives completion C, and how do I normalize this? So, this is normalized by taking mod of V alpha and squaring it, right? Because a complex place is a set of two places, right. There is sigma and sigma bar, or V and V bar, and so somehow that is taken into account when you put square here. So, what we get with this normalization is the following. So, proposition, this is called product formula for any alpha in k minus 0, product over all V is equal to 1. So, V varies over all finite and infinite places. Okay. So, let me go back to the previous, these are called finite places and these are called infinite places. Another name for this is kind of Archimedean places and non-Archimedean places. Okay. So, so this is an infinite product in principle, but most of the almost all but finitely many terms in here are 0. And the proof is really very easy. If I take norm, okay, maybe I'll give a few more steps. So, if I take alpha to be P1 to the M1 and so on, PR to the MR, PI's are prime ideals and MI's are integers, then valuation of alpha with respect to PI is norm of PI to the minus MI. Valuation of alpha with respect to any other thing is just 1 if Q does not belong to P1 up to PR, okay, and product V varies over infinite places. This valuation of alpha, this is equal to norm from K to Q of alpha, I mean element alpha, not the ideal alpha. So, let me write it like this. Okay. But we have proved earlier, we have proved that if I take the if I take norm from K to Q of alpha and I take its modulus, this is same as norm of the ideal alpha, right. So, on this side I have actually this should be mod, right, because it was product over mods of all those things, right. So, this should be V dividing infinity. So, this is another way to write it of valuation of V. This is equal to product V not dividing infinity valuation of V inverse, right. That is what the norm of this thing is. This is product over all I going from 1 to R, norm of Pi to the power Mi, and so that gives me this. Hence, valuation over all V, this is equal to 1. That is what the product formula is. So, the product formula tells you something very nice. It tells you that for elements of K, this you have this very tight thing, right. They are all, if you take valuations with respect to every place and take a product together, you get 1. Okay. So, next we want to do Hensel's lemma. It's a way. So, it's a way of finding roots of a polynomial by using roots in finite fields, right. So, what I want to do, so idea is the following. So, let f of x be an element in O sub p of x if there exist. So, what I can do is I can consider, so take image of f of x in OP mod p sub p of x, and now I will write this as k sub p, right, because this is it is canonically OK mod p, and call this image, so say this image is f bar now. If there exists alpha bar in k sub p such that f bar of alpha bar equals 0, can we get alpha in O sub p such that f of alpha is equal to 0. So, that is the question, right. And of course, the answer in general is no, we can't get such a thing in general, but there is a very nice condition on f that will tell you how to do this. So, before giving you the statement of Hensel's lemma, let us look at an example. Okay. Yeah, let us look at an example. So, here is an example. Consider p equal to 7, right, the prime number 7, and consider x squared minus 2 in z7x. So, maybe I should write the same x in both places. Right, this is my f of x. Right. So, if I take x equal to 3, I get f of 3 is equal to 9 minus 2, which is 7, which is congruent to 0 mod 7. Okay. So, f bar of x in f7x has a root in f7, right, namely namely 3, right, or 3 mod 7, sorry, f not f3, f7. Okay. So, can we get a, so clearly, I mean, of course, remark there does not exist alpha in z such that alpha squared minus 2 is equal to 0. So, that is kind of clear. We again learned this in high school that square root of 2 is an irrational number. So, not only does it not exist in z, it does not even exist in q, right, but we can find alpha in z7 such that alpha squared minus 2 is equal to 0, right. So, how do we do this? Okay, so, that would be the question. So, how? And of course, the construction is analytic. Okay, so let us look at how we do this. Okay, so so alpha 1 is in OP such that alpha 1 bar is equal to 3 in, sorry, maybe I should not write OP here, unnecessarily complicating things, in Z7 such that this is equal to 3 in F7, right, which is Z7 mod 7. I will write it this way, right. Now, I want alpha 2 in Z7 such that alpha 2 bar in Z7 mod 7 squared satisfies the following. Yeah, let me not write it in terms of bars, okay, so because that would be confusing, such that alpha 2 is congruent to alpha 1 mod 7 and alpha 2 square minus 2 is congruent to 0 mod 7 squared. So, that is what I want. Okay. So, I have something, right, I have an alpha 1 such that alpha 1 minus 2 is congruent, alpha 1 squared minus 2 is congruent to 0 mod 7. So, this is given to, I mean this is what I start with, and I want alpha 2 which is a better approximation to the alpha that I am actually seeking, right. It is a, I want alpha 2 squared minus 2 to be divisible by 7 squared rather than just 7. So, how do I do this? Well, I take alpha 2 to be alpha 1 plus 7 times some beta 1, right. So, I do not know what beta 1 is. So, want to find beta 1 such that alpha 2 squared minus 2 is congruent to 0 mod 7 squared, but I rewrite this as alpha 1 plus 7 beta 1 squared minus 2 is congruent to 0 mod 7 squared. Now, I just expand this is alpha 1 squared plus 14 alpha 1 beta 1 plus 49 beta 1 squared minus 2 is congruent to 0 mod 7 squared. But this is already divisible by 7, this is 7 squared, right. So, all I care about is alpha 2 squared minus alpha 1 squared minus 2 plus 14 alpha 1 beta 1 is congruent to 0 mod 7 squared, right. But now I know that alpha 1 squared minus 2 is divisible by 7. So, 7 divides alpha 1 squared minus 2. So, I can, so what does this mean? Alpha 1 squared minus 2 is 7 times something, some other gamma 1, okay, for gamma 1 in Z7. So, I can rewrite this as 7 times gamma 1 plus 14 alpha 1 beta 1 is congruent to 0 mod 7 square. But now there are the left hand side is divisible by 7. So, I divide by that and I get 2 for 1 beta 1 is congruent to 0 mod 7. So, I want beta 1 which satisfies this, right, which means beta 1 is congruent to minus gamma 1, right, 2 alpha 1, yeah, mod 7. But 2 alpha 1 mod 7 is equal to 6, which has an inverse mod 7, right. So, I can take beta 1 to be 2 alpha 1 inverse times minus gamma 1 mod 7. So, this is the beta 1 I want. This is the beta 1 we want, right. So, that is how you find alpha 2. So, that is just the first step. Now, let us say we have found alpha n such that alpha n is congruent to alpha n minus 1 modulo 7 to the n minus 1. Okay. Sorry, yeah, let me actually do the following. So, such that alpha to the n squared minus 2 is congruent to 0 mod 7 to the n, and then alpha n is congruent to alpha n minus 1 mod 7 to the n minus 1. So, and then we want alpha n plus 1 such that alpha n plus 1 squared minus 2 is congruent to 0 mod 7 to the n plus 1, and alpha n plus 1 is congruent to alpha n mod 7 to the n, right. So, again we use the same strategy. We take alpha n plus 1 to be alpha n plus 7 to the n times beta n. So, want beta n such that alpha n plus 7 to the n beta n squared minus 2 is congruent to 0 mod 7 to the n. Yeah, and we just play the same game again. So, I expand this out, I get alpha n squared minus 2 plus 14 alpha n beta n plus 7 to the power this should not be 14, this should be 2 into 7 to the n, and this would be 7 to the n beta n squared congruent to 0 mod 7 to the n plus 1. But this is 0 mod 7 to the n plus 1, right, and this thing is divisible by 7 to the n. So, I can rewrite this as alpha n squared minus 2 by 7 to the n plus 2 alpha n beta n is congruent to 0 mod 7, right. And again this thing is invertible modulo, sorry, not this thing, what am I saying? I do not care about whether this is invertible or not. All I care about is alpha n is congruent to alpha 1 mod 7 is invertible mod 7, and so we can uniquely find beta n. Okay. Now, we have a sequence alpha 1, alpha 2 and so on in Z7, and this is a Cauchy sequence. Hence, it has a limit because Z7 is complete. Right, and that is how you get alpha in Z7 such that alpha squared minus 2 is equal to 0. Okay, so, this means that square root of 2 is contained in Z7, right. So, that is an amazing thing because we have done it using limits. We can't do this in Z, that is why we do not get square root of 2 in Z because it is all discrete. Right. So, I hope this example illustrates for you how to how this limit process works and how you approximate roots in p-adic numbers. So, this is the thing that we will generalize next time to prove Hensel's lemma. So, I will give you two versions of Hensel's lemma. One is about finding roots, another is kind of does not quite feel like finding roots, but factorizing polynomials. Yeah, so we'll see the finding roots one first, and then we'll prove a generalization. We'll call both these things Hensel's lemma, but that's going to be our important tool for working with p-adic numbers. Thank you.